Welcome to this video. Today I will talk to you about the involutive Markov categories and the quantum definetti theorem. This is a joint work with Tobias Fritz, and I will try to make clear the ideas and how this relates to Markov categories in the classical sense. So Paul already covered a lot in his other video on this channel. So my idea is to kind of grow from that and trying to give you another perspective, which is basically less string diagrammatically associated, but still very important. And basically, we want to consider more functorial properties. Okay, so first of all, let me give you just a highlight of this presentation. The first part, we will start with the classical framework. So for those of you who have not seen the video made by Paolo, which you can of course recover from this YouTube channel, we are gonna give an idea of the classical framework and maybe just skim through some details which we don't really care about this much in this presentation. And then we will move on to the quantum framework and see how they are connected to each other. And actually the quantum framework should be a generalization of the classical framework. And then at the end of this introduction, we will finally use these two frameworks to talk about the definetti theorem. And actually, we will use the classical framework to understand how the statement should be, and then we will discuss what happens in both the classical and the quantum framework. So, without further ado, let us start. And before starting, I just want to remind you about string diagrams. So, with a string diagram, we mean just a new notation for morphisms in a category. So, if you start with a morphism from A to B, you can now write it with this like boxed phi, and we will have the input, which is gonna be below, and we're gonna have the output above, and these both will be just lines. And now if we compose, we just simply add this new composed morphism above our previous one. Another important feature of string diagrams, and the reason why they're used so much, is how they connect with the monoidal structure. So when we consider the monoidal structure, we have also this parallel compositions called like this, because we basically consider them to be independent. So on one side you have phi, and on the other side you have psi. And also very important is that since we have a symmetric structure, then we also have the swapping, and this is of course given by two lines crossing. Okay, so now let me give an idea of the classical framework. And to give an idea of the classical framework, instead of going directly to the definition, we will take the approach also discussed by Paolo, but a little bit different, and we're gonna talk about finite sets. So when we consider finite sets, things are much easier, and here we want to understand what are probabilistic morphisms. Okay, so how can we move from one set to another in a probabilistic way? And what does this mean? Well, basically what I mean is that I want to move from one set to the other with some probability involved. So this is not a deterministic function, i.e. just a function, but it's going to be a function with some perturbation. And this is exactly the concept of Markov kernels. So for finite sets, this is exactly what we require. So for each point, okay, we will assume that we will reach the target with probability 1, but of course we're gonna just have a probability associated to each point. So for instance, if you look at the slide, you will see that we have 50, the first point, okay, the one above, is gonna go 50% of the time in one point and 50% of the time in another point. And then the other one, 70% and 30%. So we kind of have this idea of moving in a probabilistic way from one finite set to another finite set. Markov kernels are very good. They also allow composition and tensor products. Basically, composition is given by a Chapman-Kolmogorov equation, while the tensor product is given by multiplication of the probabilities. We do not want to go into the details, but this is a symmetric monoidal category. And the things that I are described are exactly how you define composition and parallel composition. But the important thing that we want to discuss here is that there are two very important morphisms. The first important morphism is the deletion. From each object, we can go to a singleton in only one way. If you think about it, simply like you take a point in A, and now you want to associate to A probability on the singleton. What kind of a probability can you associate? There is only one, right? And that one is going to be, with probability 1, the only element of the singleton. So basically what happens is that this map deletes the information on A. So we can just disregard what is happening on A, and we can basically move on with our lives. Also notice that this idea of total probability to be equal to 1 actually reflects the fact that whenever you take a Markov kernel, okay, and you apply the deletion, this is exactly as deleting everything from the beginning. Because basically, if you look at this composition, this is gonna be clear that it is just telling you that phi actually is like a probability map. So every point is associated to a probability, which is whose total measure is 1. Okay. The other very, very important morphism is the copy, which here is just simply the diagonal. Okay. So you start with an element, and now you get it copied 2 times. And the idea under this is that we can deterministically copy the information on A. And this should be kind of obvious, because this map, I mean, I don't think I have to argue the fact that like honest functions will always be Markov kernels, okay, like in a trivial way, so to say. And so the copy, since it is described as an honest function, is gonna just be a deterministic idea on this category. But not only that, actually this map allows us to say when a morphism is deterministic. So basically determinism in this category of finite sets, okay, is detected by the copy in this way. So if you have phi times phi and then you apply the copy, this is exactly equal to the copy composed with phi, and this is if and only if phi is deterministic. Another very important thing is that the copy allows us to describe almost sure equalities. Here I don't want to go into the details of this, but as you can imagine, this thing is very, very important for probability theory, and so we get a very nice insight on what we can do in the categorical perspective. However, here we will not use almost sure equalities, but the fact that we can describe determinism in this way will come up, and I will also give the definition in the quantum framework, and we will see that it is basically the same. Okay, so what do we have in this example of this category? We have our objects, we have our morphisms, this symmetric monoidal category, and then what do we have? Well, let's just state it step by step. So a Markov category, okay, will be exactly as for finite sets, as we just said. We will have a symmetric monoidal structure. So it is a symmetric monoidal category. And then we also said that the deletion is the only map, okay, going to I, which is the singleton, which is actually the monoidal unit. So what do we ask? We ask for I to be terminal, okay? And then what we want? Well, we want copy and deletion. Okay, these are the three ingredients to get a Markov category. Now, the important thing to say is that, as Paolo already said, if we drop the terminality of I, we get something which is more measure theory than probability theory. And so probability is not said to be, the measure is not equal to 1 for the total space. But here, for like probability, it is very important to have I, which is terminal, and we will use it, well, not explicitly, but it is very important that it is there. Okay. And okay, so I mean, symmetric monoidal category, it's okay, we can understand. Terminal, okay, but what does it mean for a copy and a deletion? It's not just I'm marking two morphisms and we don't require any like kind of property on them, right? Just it's not sufficient to just have a type morphism, okay? So then what we want is that the copy and the deletion will give us a commutative comonoid. So for those of you who do not know what a comonoid is, well, it's the opposite, the dual notion of a monoid. Indeed, if you look at the copy is defined from A to A times A, okay? But actually, if you think how do you define a multiplication, well, you go from A times A to A, right? And basically, then we have to require the properties of a monoid, which is associativity, okay? And associativity is simply like if you copy and then you copy the first, then this is the first copy, then it is the same as copying and copying the second. And the deletion also is basically the opposite of a unit. And so we can say like if you multiply with the unit, you get the identity, right? And you can kind of require all these properties. And in Paulo's talk, you will see this made better and more explained. To me, the essential feature is commutativity, which is why I've written this diagram. So we have that the copy is equal to the copy swapped. And this is very, very important. And it's also telling you something that it's, I mean, clear for probability, which is that classical probability is intrinsically commutative. And from this perspective, you can kind of see that is very natural because, I mean, the diagonal is not gonna really change if I swap, right? It's gonna be exactly the same. And so there is nothing like very important if you want, but also at the same time, it is very important because now we understand that algebraically, probability is gonna be like a commutative side of the theory. And we will come back to this in just a matter of seconds. But before doing that, let me just give a very, very fast idea on our main example for the classical setting, which is standard Borel spaces with Markov kernels. I don't want to dive into the details of this category, but the first important thing is that standard Borel spaces are the spaces of probability which are well known and well used in probability theory. Markov kernels are the generalization of our Markov kernels for finite sets. Also, in this case, I don't want to dive into the details, so if you want to know more about this category, please also check the Paulo's video. Here, for our sake, let me also just say, if you don't know what a standard Borel space is, well, we have Kuratowski's theorem that really helps us out, because any standard Borel space is measurable isomorphic to R, Z, or a finite set. However, keep in mind that measurable isomorphic is not as well behaved as you may hope. Like, for instance, R is going to be measurable isomorphic to Rn for any n. So this is also something to keep in mind. Now we can move to the quantum framework and trying to understand how our idea of Markov categories can be used in the quantum framework. So the first thing, I said how much it is important, this commutativity, and the reason why is that whenever we are in the quantum setting, we have a non-commutative setting. So we will have something which is commutative, of course, but we also will have way more objects, and many more will be non-commutative. Okay. So a question is, how do we control non-commutativity? Because, I mean, we can also say just simply disregard the last action. So, like, take a require it to be a commanoid, but do not require commutativity. But that's not very good, because string diagrammatically you want to have a theory that really help us understand what's going on and also help us prove significant things. And as it turns out, when we want to consider like string diagrammatic reasoning, we want to understand how non-commutative stuff will be behaved. So we want to control non-commutativity. In order to control non-commutativity, we use involution of morphisms. So the involution will send a morphism of a certain type to a morphism of the same type, okay? And we will denote it with a bar over it, and we will never come back to this notation. Like, I mean, you will see it appearing. So please bear in mind that this overline is going to be used for the involution. And we require that the involution of the copy will be is actually equal to the swap of the copy, and also the involution of the deletion is going to be the deletion. But this is obvious basically because we have that the monoidal unit is terminal, so like you don't have another morphism, right? So the first one is exactly how we will control the swapping, because now we have an idea on how like the swapping is gonna tell us, okay, a story on adjoints, or like the involution of this involution of morphisms. So now when we will restrict, and we will do so to morphisms such that phi is equal to phi bar, okay, then we will see that this non-commutative thing using the involution is gonna come in handy. I mean, we are not gonna see it properly in this presentation, so sorry about this, but I think you will get an idea in a matter of some slides. So now, basically, from this idea of controlling non-commutativity, okay, we can define involutive Markov categories, which have the same structure as before. So we have symmetric monoidal category, I is terminal, we have copy and deletion. This gives a commanoid, but not a commutative commanoid. And then we add this involution, and this involution will control the non-commutativity. Okay? So this is how I imagine it in my head. And as I said, this is a very, very important notion, so it's important that we just consider it immediately. So phi is called self-adjoint if and only if phi is equal to the overlined phi. Okay, and for those of you who already know about sister algebras, Hilbert spaces, yes, this is exactly a self-adjoint morphism, but we will say something more. Just bear with me for the moment. A first very important remark that you may guessed from the previous slide is that a Markov category is basically an involutive Markov category with trivial involution. Of course, you can also equip your Markov category with a non-trivial involution, and you possibly get an involutive Markov category depending on how this involution is behaved, right? Because it's gonna be at that point, since Markov categories have a commutative common structure, it means that also this involution should respect the copy. So yeah, but this is not exactly what you have in mind. So because for us the involution is something that we add to control the non-commutativity. Okay, so Markov categories and involutive Markov categories should be thought of as like Markov categories, sorry, should be thought as involutive Markov categories with trivial involution. Okay. A very important question is that can we still use string diagrams? Because in Markov categories, all of our structure is defined using this copy and this deletion and using rules between them. So you can write basically everything you have in your category using string diagrams. But here, it seems that we don't, because we have this involution of morphisms. Actually, what happens is that you can enlarge our category and you can get a string diagrammatically approach, and this is exactly what Persigna did when he introduced quantum Markov categories. So involutive Markov categories are the same of those, and this is proved in the first chapter of our paper. So we are very happy that we can use string diagrams, but actually we do not really care for this general setting, and so we will see that, I mean, involutive Markov categories have the ability to just cut out some part of the information you don't really want to investigate in quantum Markov categories. So this is also like another point of view. Okay, so there is a benefit to consider quantum Markov categories, and there is a benefit to consider involutive Markov categories. And I think for this topic and our talk, involutive Markov categories are to be preferred. And we will see that when someone wants to consider like functorial approach, this is going to be very important. But also the remark above, so Markov categories are involutive Markov categories with trivial involution. This is not true like for quantum Markov categories, meaning that Markov categories are not quantum Markov categories. So that's another thing to keep in mind. And now that we have the idea of our example settled, let me go through our main example. So first of all, let me just give you a brief story of quantum mechanics. I mean, also quantum probability. Everything that is quantum is probability. So this is a little bit debatable what exactly this is. Let me just say it is quantum probability. So we start with a Hilbert space H, and this is the mathematical concept associated to quantum system. And now when we consider bounded operators, this basically we are consider all possible observables. Although someone may argue that observables should be just self-adjoint or projectors or whatever, for the sake of our argument, bounded operators are the idea of all possible observables. And then we have sister algebra. A sister algebra is just a choice of these observables. And sister algebras are what we want to consider. So let me just give you more details on a sister algebra. So a sister algebra is first of all an algebra over the complex numbers, which is contained in bounded operators of a Hilbert space. So it is a choice of observables, which is actually also well behaved in two ways. So the first one is that it is non-complete, and the second one is that it is star closed. Okay. So non-complete, I hope you can understand what that is. We are considering bounded operators, so you have the operator norm, and now you just ask the sister algebra to be closed under that, to be complete under that. And star closed, well, there is an operation on operators which is the adjoint. Every time you have an operator, you have its adjoint. And this is given by Reed's representational theorem. I don't want to dive into the details of that, but let me just say that for square matrices, okay, this star operation is just given by taking the transpose and then taking the conjugate of all entries. This is also called this is also called the adjoint, of course, and whenever you have a matrix which is equal to this to its star, then this is called self-adjoint or Hermitian. Maybe you already heard these terms, so that's the reason why I said that. Okay, now we can try and describe what is the involutive Markov category associated to sister algebras. And our idea is that we want to consider sister algebras with formal opposites of unitrilinear maps. So first of all, the unitality that we require, so unitrilinear maps, okay, is gonna tell us that our monoidal unit, which is the complex numbers, is terminal. Okay. Yeah, we will see why we want formal opposites of unitrilinear maps in just a second. But first, let me also say that the star operation that we have with sister algebras will give us the involution. So we can define the involution of any morphism phi to be to send x to phi x star and then star. Okay. And now demultiplication of the sister algebra will give us the copy morphism. And here we see why we consider the formal opposite, right? Because as we said, the structure of a Markov category and also of an involutive Markov category is given by this copy. This copy that we, together with the deletion, give us a comonoid. But here we have a monoid, right? So we just invert the arrows, and now we have that the multiplication gives us a copy morphism. However, there is a problem. Why is there a problem? Because sister algebras are norm complete, remember? So what happens is that one should check if the multiplication is bounded. And as it turns out, it is not. Or better, it is if the sister algebra is commutative, and also like finite dimensional sister algebras will have like boundedness of the multiplication, but that's almost meaningless to us because we want to consider like sister algebras, not just the finite dimensional things. And as soon as you go in the infinite dimensional situation, the multiplication will be unbounded, completely unbounded. And there is already an example in Parzignat paper on quantum Markov categories. Okay, so to fix this detail, what we can do is notice that the multiplication is still like here the multiplication is not bounded when we consider like an idea of a tensor product, okay, and so we have our two sister algebras, we want to tensor them, and if we want to tensor and obtain a sister algebra associated to this tensor, this is where we need to use boundedness of our maps. So the idea now is, although the multiplication is not defined completely, it is defined on the more natural tensor product, i.e. the one that we have before passing to the norm complete ones. Okay? And now if we consider this thing, we have that the multiplication is densely defined. And this is also something that really happens in quantum probability, that we want to consider things that are densely defined. Okay? Generally they are also bounded, but here it's kind of also not real. So basically we can consider things that are like dense in sister algebras and that are also algebras, okay? And one can consider this situation. And this is exactly what we do in the paper, but for our sake, we can just consider sister algebras to be the objects, okay? And I will maybe sometimes say, remember, these are not exactly sister algebras, but seriously, if you do not know about sister algebras, for instance, it is not as important. If you do know about sister algebras, what we are going to use as objects are what are called pre-sister algebras. Basically, you have exactly the same requirements and you just drop the completion. So that's how you can consider the objects here. Okay, so now we put all this situation under the carpet and try not to talk about it. And since we have two standard ideas of tensor products, the minimal tensor product and the maximal tensor product, we define two different categories. The categories C star PR min and C star PR max. And this C star PR is, just to tell you about the notation, is because instead of just considering like this dense subalgebra, we generally consider it together with the sister algebra. So we have this C star pair, and that's the reason why we use PR. So the notation will be consistent to the article, okay? But we will just talk about sister algebras, okay? I hope this is not confusing, but also to keep track about these density things for someone who may be well versed to sister algebras seems utterly unnecessary, and we will see why when we want to consider exactly like probability ideas. But for the moment, actually, what happens is that these two categories that we wrote separately are actually isomorphic, okay? And this is because unit or linear maps do not care about topology, right? So we do not have a distinction. But as it turns out, we will see a distinction coming up, and we will talk about it. So as promised, we now can define deterministic morphisms for the involutive Markov setting. And so a morphism phi is deterministic if it is self-adjoint. So phi is equal to overlined phi or bar phi. And also we have that phi is copyable, so it commutes with the copy in the natural way. We already saw that for finite sets we have honest functions as deterministic ones, or better than so we already said. And actually this generalizes to the case of Borel-Stock, and we get measurable functions. In the case of sister algebras, we have star homomorphisms, which are homomorphisms, as in like for algebras, and star homomorphisms are just preserving also the star, okay? And also, let me say that we will denote with C that, the subcategory of deterministic morphisms of C, okay? So this is just to remind you of some notation that will be important after. Also, I will mention it when it's gonna happen, but if you remind it yourself, it's better maybe, when I don't remember the notation in a presentation, generally I'm like very doubting myself for some parts. So if you remember this notation, it's gonna come in handy. If you don't, no problem, because I'm gonna say it again. Okay, a very important thing about the deterministic side is that one can prove that A is a classical object if and only if the copy is deterministic. And this is basically true because the copy is deterministic if and only if it is self-adjoint. But being self-adjoint means that it is equal to its involution, which what it means? Well, the involution of the copy is by definition of involutive Markov categories the swap of the copy, right? So this is why this is true. Okay? But also for the non-commutative side is very, very far-fetched that this copyable requirement will hold. So that's also important to say. So now to give you an idea on why star homomorphisms are also like a deterministic choice, I want to tell you about the Gelfand duality, because it's a theorem that I actually love. There is like this connection between commutative sister algebras with star homomorphisms and the dual of compact outer spaces with continuous functions. Okay, so like it has an idea of determinism, like continuous functions are very deterministic, right? And we will see that actually this becomes also like true for the probabilistic side. Okay, another very, very important concept that we need to that is important to consider when we go to the quantum side is compatibility. Remember that two observables, okay, are compatible if they can be measured simultaneously without affecting each other's measurement. What does that mean? Well, it means that basically they commute, okay? So you have your observable A, you have your observable B, and now you say that they are compatible if A times B is the same as B times A, okay? And well, now we can generalize this to morphisms, and we say that two morphisms are compatible if these string diagrams are equal. So we have the copy, we put phi on one side, psi on the other, and we say that this is equal to putting first psi, then phi, and then swapping them. This, for sister algebras, this means that we are saying that phi of B times psi of C is equal to psi of C times phi of B. So exactly the idea of observables being compatible, okay? And actually what turns out to be the case, and really telling us the story that we have above, so they can be measured simultaneously, is that whenever phi and psi are self-adjoint, then this morphism is self-adjoint. Another important thing is that phi to be autocompatible means that the algebra generated by the image of phi is actually commutative. Okay? So compatibility is some sort of like when things behave in a classical way, at least between each other. Okay? That's how I will put it. If they are not compatible, of course, hell will break loose. We have no idea what is going on, and in general, this is also kind of well known for the theory, although maybe not stated as this diagram above. So it is kind of this is related to notions of compatibility in quantum probability, okay, but maybe they are not expressed like this, and they can be different. I mean, in quantum probability there are different notions of compatibility, and but this is the natural one for us, and as it turns out, it will be important also to describe what is the idea of probability for the quantum setting, because we have some sort of a problem for the involutive Markov categories, okay? And now I want to discuss this a little bit precisely so that we can finally understand why I am saying the probability setting and I'm not saying like the involutive Markov category. Okay, so first of all, remember that we said that the copy copies the information A deterministically. We said this at the beginning with finite sets, and this is basically the idea that one wants to have when we are considering the copy and we want to, copy the information. We want to do that in a way that is well behaved, so deterministically. But also, we said that the copy is deterministic if and only if A is classical. So, I mean, what's the situation when A is not classical? And actually, there is a very famous theorem that, from this perspective, seems kind of like almost implied by these two considerations, but of course it is not. That is like the no broadcasting theorem, which is there is no copy morphism for non-classical objects. Okay, so like when you consider quantum probability, okay, you cannot copy in a well behaved way, and actually for people in quantum probability you cannot copy, like there is no copy morphism, okay, literal none, okay. But as it turns out, we have a copy, right? We have the multiplication. What does that mean? Does that mean that our multiplication is bad? Does that mean that people in quantum probability do not know that there is multiplication between sister algebras? It means, of course, the first one. So our copy is very bad. So we want to completely disregard the copy. And actually, the probabilistic setting will be a subcategory of the involutive Markov category. Okay? And so now we want to understand what exactly this probabilistic setting should be for sister algebras, right? Because at this point we understand that like unit or linear maps cannot be the right setting because the no broadcasting theorem does not hold there. So there is like not a real interpretation in a probabilistic sense. So remember that a probability satisfies normalization and positivity. Normalization, we already discussed what it is, and its unitality. Okay. Positivity is a little bit more complex for sister algebras, but the idea is that in a sister algebra you can define what a positive element is, and if you consider matrix algebras, for instance, this is exactly like the notion of a positive semi-definite matrix. Okay, and now the idea is that you want your morphisms to kind of preserve positivity, but you want them to preserve them in a good way. So to preserve them in a good way, it means also stability under the tensor product. And that's the reason why we say that a completely positive unital map is a unital thing, okay, which is stable under tensoring. A very important thing is that a positive unital map, okay, is just a unital map preserving positive elements, and this is actually unital contraction, okay? It's a theorem. This is not like immediate, but it's also like not impossible to prove it. And we want this additional thing, which is to be stable under tensoring, because when you have matrix algebras, the situation is much more complicated. And so when you tensor things, you may end up with things that are not positive. And one example of a positive unital map, which is not completely positive, is just given by the transpose. So as you see, something very natural, and yet it completely fails to give you what you want. Okay, so these maps, which are the right ones because we want them to be stable under tensoring, otherwise we don't even have the symmetric modular category, okay, will give us two different subcategories, right? One is in the category associated to the minimal tensor product, and the other to the maximal tensor product. and we are fine. Also notice, however, that we tried to not consider the norm with our notion, but we end up with contractions, which are very telling you that the norm here matters, right? Before we said that the two categories, the two bigger categories, are isomorphic. And here is the moment where I tell you that the two subcategories do really care about the choice of norms because we are considering contractions. And here is where the two categories are not isomorphic anymore. So we are basically, they are basically in the same category, but they still are completely different in this setting. Okay. And that's the reason why we actually distinguish them. So a very important thing is that we have probabilistic Gelfand duality, because if you want to say that these are the right, so to say, probabilistic maps, then you need to motivate it. And I feel this duality really motivates it. Commutative sister algebras with completely positive unital maps are exactly compact auto spaces with continuous Markov kernels valued in random measures. And so we are happy that we are actually considering something which is probabilistically relevant also for the classical case. Okay, because the category that you see on the right is actually already studied in the first article of Tobias Fritz, who started the whole branch of Markov categories. Okay, so now we can define what a picture is, and a picture will be something that mimics the behavior of Markov categories, but also of our completely positive unital maps. So we say that a picture is a symmetric monoidal wide subcategory of C, such that blah blah. At the moment, let me say something, because we already said something which is very subtle, which is wide subcategory. So we want every object of C to be also in D. So we do not want to disregard objects. We want to consider all objects of C. And now we say that our picture is like this. Okay. This is basically because if we do not want to consider an object on C, just disregard it at the beginning of the whole setting, because it's not going to be relevant. But more of this interpretation in the next slide. Now let us go into the detail of what a picture requires. So we first of all want all morphisms to be self-adjoint, okay? Because well, we do not want the copy unless it is deterministic, right? So this is, if you want, our first understanding. But also positive unital maps are self-adjoint. So then we want the deleted morphisms to be contained in D, and this is because although we don't have the copy, the deletion is very much more important. And basically there is also people considering quantum probability without the notion of involutive Markov categories, and this is something called like semi-Cartesian probability. This is a very little branch, but in that setting you still want the deleted morphisms to be there. In particular, you want terminality of the monoidal unit also in your picture, in your subcategory. And then we have the technical condition, which you cannot state for this semi-Cartesian probability, okay? And we say that if phi is autocompatible and psi is compatible with phi, then we have that the copy morphism where we add phi on one side and psi on the other side is still in our picture. Here I'm of course assuming that phi and psi are morphisms in D, okay? And this requirement is very technical, okay? But it is important because it allows us many reasonings that we had to do in the paper. But okay, it is important to understand how these technical requirements give you a Markov category. So first of all, let me just say that Markov categories, CPU min and CPU max, are pictures, and this is exactly what we want, right? We want this picture to be like a quantum version of Markov categories, more than involutive Markov categories, right? Because Markov categories are are probabilistic, a probabilistic theory. So here we want the quantum probabilistic theory, and we want, of course, the two things to be like the classical probability to be a subset of quantum probability. So it is important that Markov categories are pictures, and of course also the examples that we have, completely positive uniton maps, should give you a quantum probability setting. Okay, otherwise the definition is basically nonsense. We're doing category theory, so maybe that's fine, but we still want to make it sensible. So let me just say that if you have a picture, okay, and instead of an involutive Markov category, you have a Markov category, okay, then our picture will be a wide Markov subcategory. Because think about the technical requirement. Phi to be autocompatible means that if you take the copy and then you do phi and phi, this is equal to getting the copy, doing phi and phi, and then using the swap. But since the copy is commutative, every morphism in a Markov category is autocompatible. So the first thing does not require you anything. And in particular, you can consider phi to be the identity. And now, guess what we do? We also consider psi to be the identity. So basically, of course, the identity is compatible with the identity, because we already said that the identity is autocompatible, right? This, of course, let me stress this, we are considering Markov categories, okay, where commonites are all commutative. This tells us that our technical requirement requires the copy to be in this subcategory, okay? So our picture is really expanding on the notion of Markov categories for the classical probability, with the additional feature that now we have a way to discuss also the copy and how this copy pops up in the quantum world. Okay, so let me give a remark. In this presentation, we started with an involutive Markov category, and then we defined our picture. But maybe it's more sensible to give another version of this story. So the idea is that, generally speaking, you want to just consider your setting of probabilistic, your probabilistic setting, okay, which is your category D, and now you want to equip it with an abstract setting where you can copy, and so you can kind of understand when things are compatible and how these things relate to each other, and trying to give a like a well-versed theory, which makes I mean it doesn't make more sense, but it is more interesting and insightful. So in this with this idea in mind, basically we equip D with an idea of generalized morphisms and an abstract framework. And this is what we want to do. Okay, so before going to the definetti theorem, let me also talk a little bit about what we did. So with our picture, we have a tensor product, we have objects, we have generalized morphisms, which are this abstract framework we just said, morphisms, and also deterministic morphisms, which are the deterministic morphisms, of course, of the involutive Markov category associated to D and restricted to the picture. Okay. Now, for Boralstock, it shouldn't come as a surprise that well, the tensor product is the Cartesian product with the sigma algebra generated by rectangles, as one expects for from measure theory. Objects are standard Borel spaces, as we already said. There is no real reason for us to expand the morphisms, right, in Borel-Stock, because this is already a Markov category. So generalized morphisms coincide with morphisms and are Markov kernels, as we already said, while deterministic morphisms are measurable maps. Concerning our quantum setting, we have CPU min and CPU max, which have the minimal tensor product and the maximal tensor product respectively. But then all the other things are the same. So we have sister algebras, okay? Remember that these are not exactly sister algebras. These are dense subalgebras, but who cares, okay? Then we have unital maps as generalized morphisms. Morphisms are completely positive unital maps, and deterministic morphisms are star homomorphisms. And let me say that I'm a little bit misdirecting you in this slide, because it is true that morphisms are completely positive unital maps in both the minimal and the maximal setting. However, this notion is sensible to which tensor product you consider, okay? So remember this. So it's not giving you exactly the same morphisms, okay? But they are defined exactly the same. And now we can move to the Finetti theorem and try to understand how our framework is able to give us a statement, and how we can understand the proof a little bit. So first of all, a rough idea. The definetti theorem tells us, roughly speaking, that whenever the probability of an infinite sequence of outcomes is independent of their order, such outcomes are drawn independently from the same underlying distribution. Okay? And now, instead of let you understand what this means, we are gonna boil it down in several steps. So, first of all, when we consider probability of an infinite sequence of outcomes, well, maybe we want to understand what an infinite sequence of outcomes is first, right? So here probability, just to tell you, the probability will be a morphism, okay? And I have not said this before, but consider the case of finite sets, for instance, and you have these perturbed functions, right? So now if you start from a singleton, you have exactly a probability on the target. And basically what happens is that also in the quantum setting, okay, a probability will be also a map from the monoidal unit, because it's exactly what people in quantum theory call state. But for us, a probability is just basically a morphism. Okay, so I didn't want to go into these details. So we want to understand what an infinite sequence of outcomes is, and this is where Kolmogorov products come in handy. And basically, Kolmogorov products are just infinite tensor products described with limits in category theory. We don't want to delve into the details, so let me just say that we consider an to be the countable Kolmogorov power of A, and this is just like the idea of infinite tensor products that you may have in mind. And the reason why it is called Kolmogorov products is that because in Borel-Stock, a Kolmogorov product is well defined, has the right categorical description, because we have the Kolmogorov extension theorem. Now we can go on with our sentence. So whenever the probability of an infinite sequence of outcomes is independent of their order, what does independent of the order means? For us, it means invariant under finite permutation. So let me also note that whenever you have a finite permutation sigma, you can associate morphisms from an to an, which basically swaps according to the finite permutation sigma. And now we can say that our probability of an infinite sequence of outcomes is independent of their order is just this notion that we have displayed. So phi from C to an tensor B is exchangeable in the first factor if for every finite permutation sigma we have that phi and then you apply a sigma on the an side, this is equal to just phi. And yeah, okay, so we have settled the first part of the sentence. Now we want to settle the whole sentence, hopefully. So we want to say that such outcomes are drawn independently from the same underlying distribution. Okay, so we need to understand, first of all, this underlying distribution, okay? The first thing is, so we want something which will give us back our exchangeable morphism. How do we do that? We need to understand how these things factor. So this is exactly the same question as saying, like, where is this same underlying distribution defined? And the answer is on a space of probabilities. And we will say what it is in a moment. But first, I want to give you a very, very important remark, which is to put the attention and the stress to drawn independently. If we draw independently, it means that we can copy stuff, and these things are independent. What does it mean to be independent? It means that these are not associated in any way, i.e., it means that we can copy deterministically so. And we already know what that means. It means that the deterministic copy must be deterministic, i.e., this space must be classical. Okay? So, of course, this is not going to be important for Borel's talk, which is what we're going to discuss in the next slide, but it is going to be incredibly, insanely important for the case of quantum probability. So, let me start with the idea of the space of probabilities. So, in Borel's talk, we have that PA is the measurable space of probabilities of A, okay? Whose underlying setting is exactly underlying set is exactly that of probabilities of A, and measurability is defined accordingly to get two properties. The first one is that whenever you have a map from B to A, this gives rise to a deterministic map from B to PA. Think about the finite sets. You have your Markov kernel, which to each object and to each element of B assigns a probability on A, right? So then if I consider just the space of probabilities of A, it means that I'm sending each element of B to a point of PA. And this is why this is deterministic. Also, there is a map, which is called the sampling, which inverts this association. So let me just say, what is this map? Well, this map is sampling, okay? It just remember that for each element of the domain, you want to associate a probability on the codomain, right? So now you take a point in P of A, and a point here is a probability on A, and you assign a probability on A. Which probability do you assign? Well, I mean, basically this is the identity, and it kind of is so under the isomorphism we will see in the next slide, and we are actually there, so we can define this. So we say that a picture D is classically representable if for every object A there exists a classical object SA together with an evaluation morphisms, which is basically our sampling, okay, such that we have this bijection tested for every classical object B in D, okay? So as you see from this thing, if you consider what we said just before, here the evaluation you can change it with the sampling, and you see that the identity is of course a deterministic morphism from SA to SA, and now we are gonna move it to the sampling. Okay. Very important things is that Borel's talk, CPU min and CPU max are classically representable. Okay. And basically also for CPU min and CPU max, we get a probability space. I don't want to dwell into the details of that, but it happens. And so we are very happy and we can move on with our lives. But first, let me say why, let me ask, why did I change the notation? Like first I had sampling and now I have the evaluation morphism. Well, because I wanted to be consistent with the paper, and in the paper we have another notion of representability, which is one where we disregard this classicality. Okay, but of course, like for the definetti theorem, we want the object to be classical. So we want to consider SA, which is something also called the state space object. But we can also define representability without classicality, and representability without the classical restriction is denoted with PA and SEMP-A, exactly as we did before. Of course, I mean, for Borel's talk, you don't really care. Representability is classical representability. But representability, although it is not the right notion for the definetti theorem, is still very important for two reasons. The first one is that it holds. So if it holds, it's very good. And maybe it can be used in the future. Also, it is quite interesting to see, I mean, both objects are very much considered already in the theory of sister algebras. It's not that we had to understand what they were and no one really cared about this, okay? Just maybe they didn't care from this categorical perspective, but already like in a categorical perspective, somewhat. And the other important thing is that it gives us a monadic structure, this P, okay, the representability without classical restriction. This is all very not the case for the classical representability, though, keep in mind that. So for the representability without classical restriction, we have that our picture is equivalent to the Kleisli category of P restricted to the deterministic side, okay, which is very intriguing. Now we finally are able to state the definetti theorem. So we say that D is classically representable picture with countable Kolmogorov products. And then we say that for every phi from C to AN tensor B, which is exchangeable in the first factor, there exists a unique morphism phi, mu from C to SA tensor B, such that basically you factor phi using mu, and this evaluation an infinite amount of time. Now, the philosophy under this statement is that basically after an infinite iterated sequence, you can understand the underlying distribution, or more to say, sorry, you kind of know there is one, okay, but to say exactly which one it is, it's more like a law of large numbers. So just to put it out there. And the very intriguing part is that this statement is exactly the one considering both the classical and the quantum probability. And generally speaking, we don't want B involved, so we just drop B, and we have exchangeability. And also C is the monoidal unit, which is to say we want to consider just probabilities and states. But actually, and in that case, okay, we have the same statement proved in the classical probability sense and in the quantum probability sense. But now the very important thing is that it is not as difficult, okay, to extend this result for just probabilities to Markov kernels on one side and completely positive unital maps on the other side in this diagrammatic fashion, okay? But of course, now we would like to also understand how do we prove it, and can we prove it synthetically using this categorical framework. So the answer for classical probability, for the classical probability setting, is yes, yes. For representable Markov categories with countable Kolmogorov products and conditionals like Borel's talk, we can find a synthetic proof. Okay. Here I added this new term that we haven't discussed yet, which is conditionals. Okay, conditionals appear also in Paulo's talk, and it is very important. But I don't want to really give you a definition of conditionals. But do remember that when we have a probability framework, you want to condition, and this is very, very important. So in string diagrammatically, it has proven to be like the main ingredient for a lot of theorems to hold. So it is very important for the theory. Okay, so now we know that the classical probability setting is nice and it works. And this was also this is a paper from Fritz, Gonda, and Paolo. The quantum probability setting, however, is not as nice because CPU min and CPU max don't have conditionals. So you don't have the way of conditioning that you have in classical probability. So how do you prove it in the same way? Well, you don't know because you don't have conditionals. But also, will the same reasoning work anyway? Because we are considering a structure which is a little bit less nice, and like the copy is not really understood unless you have like a classical object. So this is kind of really problematic. However, what we can do at the moment is we can prove it using an argument which is half synthetic. This is what I want to give you an idea of. So the idea of the proof for the quantum setting is very nice for me. So the first step is to define a definetti object, which is like a well-behaved limit of finite permutations, and for which the statement holds. But remember, in the statement we want the state space object. Here we have just QA. Well, as it turns out, by a synthetic argument, you can show that QA is actually isomorphic to SA. So that's very important. And on the third step, we use Hulanicki and Phelps' quantum definetti theorem for states. We construct our definetti object, and using the synthetic argument, this means that it is also isomorphic to SA, so we conclude. And now I also try to conclude this presentation by telling you what we want to do next. So an important probability tool, as I was saying just 2 slides before, is the thing that we can condition probability. Okay, we can what's the probability of this event given that other? Okay, and can we get conditionals in quantum probability? And this is kind of hard. What we know at the moment, at least what I know that is known, is this result by Perzignat and Russo, which is just a preliminary result for finite dimensional sister algebras. Okay? So we are really, really restricted, and we have trouble with infinite dimensional cases. A very important thing that will make you understand why we do not even know if we can use the same synthetic argument is that in general, conditionals are generalized morphisms. They are not even good enough to be in a completely positive unital map. And in fact, in the article that you see displayed as a footnote, they actually give a sufficient and necessary condition for their conditionals to be completely positive unital maps. So in general, you have generalized morphisms. And how can you work with generalized morphisms if your classical representability concepts and representability in general is just about the picture, which do not take into account generalized morphisms. It's a very hard problem to solve. And also there is another problem, that CPU min and CPU max cannot have conditionals. Okay, they will not satisfy this property in general, and this is because already compact also spaces with continuous Markov kernels do not have conditionals. So already in the classical setting, this does not work. So we have no way to hope that this will hold for CPU min and CPU max. So the first step is finding the right sister algebras, and this is what we're trying to do with what I'm trying to do with Tobias Fritz. And for the moment, what I can tell you is that these sister algebras are at least sister algebras with a monotone convergence theorem, but we want to consider something else, a little more structure on these sister algebras. And these sister algebras are good enough so that Borel-Stock actually embeds fully faithfully on it. Okay, and this is quite important because this is not the case for CPU min and CPU max. So if this setting works in this way, then it's fine, it's nice, it's the right one, but we need to understand how we can restrict the sister algebras in the non-commutative case. For the moment, it's already hard. We would like to have a probabilistic Gelfand duality for Borel-Stock, and this seems to be achievable. And then we will try to understand what happens with the non-commutative case, although this is very, very hard and is part of the theory from, like, this is this has been studied for quite some time and seems to be very unsettled, but maybe it's because it's not really clear what you want as conditionals in general. But with the theory of Markov categories, this becomes very much more understandable. So maybe we have the hope to really fix these things. But for the time being, I am not like, I am hoping, but I'm not sure that we can do this. However, we can say something about the commutative case, and this may help us still understanding if we have a way to settle the Finetti theorem in a synthetic way, also for the quantum setting. So thank you for your attention. I hope this was a good drive through the Definetti theorem and also the quantum framework and how this relates to the classical framework. If you have any questions, I will ask Paolo to put my email in the description of the video, so you can email me if you want. Take care.